For our project, we are tasked with the autonomous race car. I'm Lewis. This is Harshal, Victor, and Jason. So in this Google Slides, we're going to talk about our goals and detailed specifications, our architecture, and then we're going to talk about a Gantt chart, our work plan tasks that we are completing, and then some details about each individual task. And then we're going to mention our budget and summary. So what are our goals? Our goals we have to make the car control itself while moving at a high speed. And then we must have some autonomous aspects with lane detection and path planning algorithms. And how we plan on doing that is with the TCNJ track, having to detect, okay, here are the two white lines where someone should be running. Stand that lane, kind of similar to the previous project, is make it go in a loop, but plan it with the lanes. And also we have to have also become remote control with the Android device. And so how we broke it up was the first semester, which was last semester, we had it. So build the chassis, make it remote controlled. This semester, more focused on building the shell, make it look pretty, and also add in the autonomous aspect. So this is our architecture. How it works with the remote control is we have it through an Android app called the Blue Dot. And then this is just the specifications of the inside of the Raspberry Pi. So we have it with the ultrasonic sensor, which is for the autonomous aspect, and then also with the camera. And then for the motor driver, that powers the wheels in the back and make it go forward backwards. And then we also have a servo motor, which makes it go left to right. Do you want to mention anything else with this? With the architecture?
All right, so there's a Python 8 framework called Blue Dot, which allows you to configure the user interface of the Android remote control that allows you to remotely drive it forward, backward, left, and right, as well as toggle between manual and autonomous modes.
This is our Gantt chart. As mentioned before, this is the fall semester. So we have 11 tasks. And as you can see, we have the tasks, the progress, and then the start date, and how many days we estimated it to be. So as you can see, we pretty much are up to task 8. 7, we just bought some ultrasonic sensors that came in yesterday, I believe. So that's pretty much complete. As mentioned, we're on to task 8 now. So this is all completed within the previous semester, which was built, like I said before, building the chassis and then making it become remote controlled through the phone. So now go next semester, we can see that where the red line is where we are today, around mid-March. And right now we're on task, which would design the neural network, which will then become the autonomous. And then once that's done, last few weeks of the semester, we want to make fine tuning just to make sure everything is running correctly for the final presentation. And yeah, and then documentation, we have to do that from the beginning of the semester to the end of the semester. So that goes on the whole year. So then right now we're about to go a little more into our task, the details of it. So for the first few tasks, we had to research and acquire the basic parts for the chassis. And then once we receive the parts, which is task 2, we then test it just to make sure we're not going to go gluing it on, if the part doesn't work, because that would just be not worth it. So after we got all the parts and we tested to make sure it ran correctly, we built the chassis, and then we had to research if we want to use the Raspberry Pi or if we want to use an Arduino, and then we decided to use that. I think at first we used the Raspberry or the Arduino, and then we switched to the Raspberry Pi. And then for our 5th one, we had to now code the microcontroller.
And these are our remaining tasks. We go from task 6, which is refine remote control and driving mechanisms, all the way to task 11, which is documentation. So the next couple slides, we're just going to break down each task individually. So the first task is researching and acquiring our parts. So the parts where we needed to build the car to begin with, we needed wheels, we needed a power source. We basically needed to just get it to function on a very basic level. So this was task 1. Task 2 is testing everything. So we got our wires, we got our power source, made sure everything was functioning properly, and then we can move on to our next task. Our next task was build the chassis. So we basically take the parts that we have, put the wheels onto the motors, put the motors onto the frame, put all the wires in the right spot, put everything together. So we have our thing. So this task was research and acquire our microcontroller. So we used, so to start with, we used Arduino microcontroller, and then we transferred all our code to Raspberry Pi. The Raspberry Pi, we like it better because of the Bluetooth connection, and that's going to come in play further on for when we're doing our remote control. So we use this Raspberry Pi microcontroller for our machine. So then this is task 5. We install the microcontroller onto our chassis and we code the driving and steering functionality. So what we did was we basically, the cool thing about the Raspberry Pi, you can use it like a computer. You just plug in a USB mouse, a USB keyboard, and you plug in a monitor. We were able to code in Python basically directly onto the microcontroller. And that's how we were able to get the driving functions and steering functions. And so task 6 is refining our remote control and driving mechanisms. So we, of course, we test our machine out, and we also developed an Android app for the remote control process. And we're able to do this using a Python library called Blue Dot. So we downloaded the Python library. We downloaded the Python library to our microcontroller, and then we used the app on an Android phone. And we're going to go into detail on how the app works later. But this is what we did. Everything is coded in Python, basically.
All right, so for the next task we were to research and acquire the sensors, mainly for allowing the car to drive itself without any human intervention. So we chose ultrasonic sensors so that it can detect obstacles that way won't collide into anything, along with the line tracking sensors to ensure it would stay within lanes. Like on the TCNJ track there, it's divided into lanes by white lines and a reddish track. So for our autonomous aspect, we're going to be using a convolutional neural network, which is commonly used in image classification applications. And we're going to be using a framework called TensorFlow to train and test our neural network. And we're going to collect our images via a camera that's going to be equipped on the Raspberry Pi. And what it will predict is the servo's rotation, since the servo, as mentioned earlier, is going to control the steering. Our next task is to allow the autonomous control. So we're going to place the sensors on our chassis for ideal operation, and we're going to add the sensor configurations into our code, along with testing the car to see if the sensors are in working order. Our second to last task is going to be finalizing the car and polishing things up, ensuring that they're operating as expected and no problems that can occur. So our final task is going to be documentation, which we're going to be taking down detailed notes on what we experience and what we do throughout the duration of the semesters. So as you can see right here, this on the picture on the left is the car design that we used in our demo last semester. It composes of a Raspberry Pi along with an H-bridge and a standard yellow DC motors, along with a portable charger, which we were using as the battery. And the motors are driven, and the motor driver takes in a PWM input from the Raspberry Pi and uses that, converts it to DC, and drives the wheel forward and backward. And on the right is our remote control UI, which we developed using the Blue Dot framework. It looks like a standard remote control. The top purple circles for driving forward, like speeding up when moving forward, or slowing down when moving forward, or slowing down when moving backward. the bottom purple circle is used for speeding up while traveling in reverse or slowing down when traveling forward. And the left and right circle buttons are for rotating the servo motor, and the central purple square button is for resetting the servo angle once it decides on a turning angle. And
So-
you notice,
So the left and the right button turn the car.
yeah, and on the bottom, and the bottom red buttons, the left one is for toggling between manual and autonomous modes. So once you toggle the red circular button, it's going to turn green, and all the purple joystick controls will vanish. And on the bottom right, you can see the red square button. That's going to seize all movement completely until you press any of the joystick controls again. So that's pretty much for emergency situations. If it's going erratically, you can just freeze all the movements. So we're currently working on refining our chassis. We used Autodesk Inventor for this, and this is an assembly of the new chassis parts that we planned. They're all 3D printed at the moment. So as you can see, there's going to be a motor wedged in between the two back parts. As you can see on right here, there's a handle that's going to be attached to the wheels, which will rotate the wheels forward and backward. We're switching to a single motor from two separate left and right motors because those tend to cause drifting because the motors may have different efficiencies if they're two separate ones. And on the front, as you can see, there is a bracket which will rotate with the servo and provide steering to our car. And these 4 items on the bottom are placeholders for our line tracking sensors, like we discussed earlier.
So here's a video of our car running.
Yeah, this is a dry run that we took last semester of our car.
Yeah, this is with the old chassis.
By the way, the camera is placed like directly on the vehicle itself, so you're getting a
facing
first
forward.
person view
Yeah,
of the vehicle.
yeah, and I used a phone camera for recording this. We haven't calculated the exact speed yet, but
Especially because we're changing out the motor and the motor systems, so hopefully it'll get much better.
Is this time-lapse video or real? No, that's real time.
It was much smaller, but with the new chassis, it's gonna be about twice the size that it is now. And compared to this, it's maybe like, Harsha, what would you say, like
it's about a foot
this
long.
big? Yeah, it's
Yeah.
like
Yeah.
pretty small. Yeah, I think it's 10 inches. The original chassis was 10 inches, right?
Actually, it's I estimated it to be like 40 by 35 centimeters.
Okay.
As you can see, if it moves straight, it does tend to drift. That's because of the motor's efficiency, the back motor's efficiencies.
Yeah, this is back when we had 2 different motors. So if either one of them was running at a different efficiency, then it would cause issues with the steering moving forward, like trying to move just in a straight line.
And this is not moving at its maximum speed, it's moving at less than that. So we changed the speed by changing the duty cycle of the PWM signals. A higher duty cycle means a faster speed, but a lower duty cycle means a slower speed. Although at really low duty cycles, the motors don't really move at all, but there's like a threshold. Actually, this is driven remote control. I'm
Yeah, we're
actually behind the
controlling this.
car.
This is on one of our phones.
Right.
Just
Yeah, we
controlling which way it's going. With the blue dot API that we showed before, with like the left and right accelerate.
yeah, and I
decelerate.
was behind the car steering it. Sooner or later, it's going to stop and drive backwards.
Our old chassis was also just too light, where all the pieces that we put on it, like the motor and the Raspberry and Pi and stuff, were weighing it down. So that was another thing that was adding to it not being able to drive straight well.
And the wheels weren't really suitable for outdoor terrain, so we had to swap those wheels.
Yes, we had to make a lot of modifications. The first semester, we were just trying to get anything that could move forward and that we can control.
So yeah, it just stopped, and now it's now I'm steering it backwards.
Your emergency stop button, does that like instantly stop the wheels? And so
Yep.
Yeah, it's a
the
kill
car
switch.
Tipping forward?
Yeah.
So seriously, emergency, don't just stop.
Yeah,
Don't
it just ceases all movement completely and resets the servo back to its 0 degree position, which
Yeah.
is pointing straight forward.
So it's like an emergency brake that also turns your wheel back to, like, resets it back to 0 degrees, like back to your wheels facing straight.
So it's not a jerk stop.
No, it's not.
And it's available in both modes, manual and autonomous. That what like currently the button that toggles between autonomous and manual mode is just a placebo, since we're still developing the autonomous control.
But yeah, the emergency brake will be available in any mode. So if it's just autonomously steering and it's going somewhere you don't want to, or if there's like an unknown obstacle, then you can just hit the kill switch.
So the race on the track, if you're on the, it's a race against time and for, right? It's not like like going through a maze where it's pretty much a straight
Yeah,
kind of.
we'd have it run the loop of the track against itself over and over to try to find the best algorithms and like just set up for the car that we can.
Yeah, this is on a phone. I put a phone camera, so it just crashed and tipped the phone over. But we are putting an integrated camera this semester.
Why did it crash there?
I think it was, I'm not sure why. I took this last semester, and I actually manually picked it up and took it back to the lab once I was done with the video.
So we've been working pretty consistently over both semesters, but there's been a couple like dips and bursts. So like a lot of the times when we were waiting for parts to come in the mail or waiting for 3D parts to print, we couldn't really do as much work as we'd like, and we were a little bit behind schedule. But other weeks we were able to put in, like when we had like something in front of us to work on, we were able to put in extra work, and it's been a pretty like roller coaster up and down experience with this kind of project. Next slide, Hart. So our budget is $400 total for our senior project. And so far, we've only spent $167.41. And here's our budget breakdown. So what was most expensive was that Raspberry Pi, because it's a really complex piece of machinery, and it costs a lot, but it has a lot of uses for us, so it really was necessary.
Yeah, and that's like the brain of the car.
Yeah, everything else we have is interchangeable parts, and some of which we're replacing with this new chassis.
And we also had $20 from our budget on PETG filament. PETG is a material used for 3D printing, and that's known for its durability and ability to handle really high temperatures. The other materials, PLA, which is pretty common, and that's known to be brittle and doesn't really work well in super high temperatures.
Yeah, so we went for the more expensive and more durable material because our goal is for it to run autonomously outside on the track. So we want it to be able to withstand some elements and, couple small collisions. So here's a QR code that you can scan and go to our website if you like, but you'll have this available after. It just gives you a rundown of our project, pretty much what you've seen here. Also gives you a little bio on all of us. Anything else you want to say about that one?
I can understand.
I have a question. The sensor, are they built specifically for this type of people?
The ultrasonic sensors are good for like measuring distances. So that way, if it's like within a certain distance, it's going to take action. In this case, if it's near something, it's going to pause and make a decision.
But they're not really built for these kind of vehicles, so we have to kind of
Configure them.
yeah, configure them and get it to work ourselves and figure out like where we're supposed to put them on the vehicles, everything like that.
I was gonna ask you, TCRT 5000, I haven't tried them outdoors yet. Have you gone out to the track on a sunny day like this and see how they work?
I think I've tried it.
You haven't tried that though.
No.
Yeah.
Let's go to the next slide.
It's an infrared with a photo transistor, but it's got a voltage comparator on a potentiometer.
One of the things we were thinking of is, at least with the infrareds, we know that they should be able to work even if we go out to the track at night. But you're right. I haven't thought of the dangers of going out there during the day
Yeah.
and the kind of wear and tear that that'll have on our vehicle. So
You
that's
can
something we
shield
should
it
put
and
on.
put it low, but that maybe, I don't know. That's interesting.
So in summary, we're looking forward to completing our autonomous race car, but we still have a good ways to go. Our remote control performs it pretty well indoor environment, but we're having troubles driving straight, but that should be fixed by the new chassis. We're about to finish that like right now. This next coming week, we have all the pieces, so we're just putting it together. By the end of the semester, we expect to realize the full implementation of the autonomous control. Yeah, as you saw, we have the whole framework set up on the Bluetooth API, and we're ready as soon as we get it working. And then we plan to test it out outside of the TCNJ track. Yeah, so if it ends up not working, like if we can't get it to work outside, we can always go back to getting it to run autonomously inside. We're going to get it to run autonomously in some fashion, but we really want it to work outside on that track. And yeah, the data is going to be acquired with the camera and the sensors mainly. And the camera just sees, like just generally in front of it. Also can pick up debris if there's like a stick in the track or something like fell.
Along with
And
capturing images for a neural network to train.
Yeah, all of that data is going to be going into the neural network. And then, Art, is there anything else you want to say?
Any questions?
What's your final motors?
I'm not sure exactly what it's called, but the back motor is going to be like, about those yellow DC motors?
The TT motors?
Yeah. Except the two distinct one, it's going to be a single one that controls the left and right, along with an SG90 servo motor, which can turn. We're expecting it to turn 40 degrees to the left or right at the maximum, since that's like realistic for a real car's steering angles. Anyone else?
Yes. So you said that you were gonna instrument things and record on the Raspberry Pi as memory all the values from the sensors.
Yep.
Are you also making any tools that allow you to review those afterwards to see what it was that went wrong, why things are not working?
That we'll still have to figure out.
Yeah, we're just about to start the autonomous aspect, so we still gotta learn playing around with it.
You haven't worked on your debugging tools for the actual when things actually trying to be autonomous, running into walls.
Yep.
Yeah, we're about to start it this week.
Very much like you were saying, I'm not sure how the Raspberry Pi does it, but for our we have that implementation, which it has a serial that shows the distances of every sensor we have, so we can see all 6 sensors.
Yeah.
And I don't know what's called serial monitor. Not sure what the Raspberry Pi would be, but that could be a fix system.
Yeah, we'll check it out.
Yeah,
Yeah,
and we
thank
already
you.
ordered like I think 11 ultrasonics, so we could place them like all over the car and have them pick up details.
Yeah. We have been measuring every 20 seconds. Just make sure it's that's well. I guess you guys can do the same exact thing with your sensor.
Yep. Yeah. Thank you.
So your goal is to be raising those truck.
Exactly.
Yes, sir.
So you have the line of sensors, what do you need to know about the cameras? What you train them on?
To have it navigate around a predetermined path, that way you can like follow its course and not drift away, and that way you'll know when to turn and
So line on the sensors for the extreme scenario.
Yeah.
Yeah, like an extra check, make sure that it's within bounds.
anyone else?
Thank you very much.
Oh, I had a question. Are you all comp sci majors or do you have?
No, we're just-
We're 2 of us are computer engineering majors, one of us is an electrical major, and one of them is an engineering science major.
Yeah, so we're all computer engineering, electrical engineering more than computer science.
Oh, right.
But it's closely like intertwined. with computer
Yeah,
science.
and
We do a lot of
computer
that
engineering
stuff.
does include some computer science courses too.
Yeah, many.
All the different disciplines work together. So-
Yeah, and we all have our own role. Like me and Jason over
Yeah.
there are the chassis design. Victor's the remote control design. He's the autonomous design.
Yeah, we have roles within the team.
How did you figure out your schedule? Your Gantt chart of all the work you have to do? Did you just say we are gonna spend 2 weeks on this and a week on this?
Yeah, we kind of like guess and check.
Yeah,
then
and
the
we
closer
adjust if things don't go as planned.
we guess and check. So the closer we get, we fix it up. Like, okay, we actually start on this date.
Yeah, you kind of got to react as you go a little bit.
All right, that's, I was like, wow, how can you know all that in advance?
Yeah, that's why some of the weeks were like above our planned hours, some of the weeks were below.
Yeah, we have to
it's been a bit
readjust
of a
by
roller
we
coaster.
readjusted also based on feedback given.
Yeah, also, especially last semester, we had like check-ins every week where they check in our senior project and tell us like either like we need to go push it a little bit or like, okay, we're in a good spot, we can chill a little bit. So,
So
yeah,
I imagine it's 20 hours a week for among all of
Yes.
you.
yeah, that's a total, we have an Excel sheet where it totals up all of our hours that we log in. It adds them up for like that's the goal for the whole team.
And you said that you changed the design of the vehicle from the first semester to the second semester.
Correct.
Yep.
Did you do that sort of retrospect, looking at what it was that was going on? How often do you do that? You do the full process and say, that's the end of the first semester, let's make a difference.
There's a little bit of both.
Yeah, a mix of both, honestly.
But towards the end of the semester, we had one particular incident where like we were at a good spot, we were ahead, and we tried to put the car outside, and then one of the motors started smoking and blew out, and that's when we knew like, okay, this format isn't gonna
Yeah,
work. We're gonna need a
and
new chassis.
and
So
the
we
wheel
started
is
designing
and the
towards
wheel at the
end.
time was weak to handle bumps, so we had to order stronger wheels this semester, along with making our chassis more durable. It's a mix of both.
Yeah.
We're mostly together and like we have like scheduled meetings, but also sometimes, I mean, so we have like an individual room in Armstrong Hall that only we have swipe access to and nobody else can get in it. So like all the stuff for the senior project is safe in there, so we just leave it in there. People can come in and work like in the middle of the night if they want to. Nothing is stopping them, and we do that sometimes. But
You do a daily stand.
daily stand-up.
I- Yeah, it is corporate speak. It's something like my software design team. We have a daily meeting, 15 minutes. Everybody says what they're working on, if they have any blockers, what they hope to accomplish that day. Do you do something like that, or are you just together, you just know what each other's working on all the time?
We also do brief each week.
Yeah, more weekly, but that sounds like a good idea. I mean, at this point with 8 weeks left, it's kind of the crunch. So it's at this point where we should be going daily. Yeah, sounds like that would be something that we should and could incorporate.
Yeah, it's most of the time like you walk into the lab and they're like, oh, hi. So you're here. What you been working on? And
We
then it's really casual.
We have a weekly meeting every Thursday, and it was every Tuesday last semester with our senior project advisor. So that kind of functioned as like giving us all the direction, like checking in and stuff. But now that we're getting towards the end of it, I think we could use more, like a daily.
What's the thing that you've learned most from this process?
Do you want a topic, or you mean like in general, or what are you looking for?
What have you learned most?
Whatever we.
We learned about like the durability of different materials, as well as the effectiveness of different ways of making it work autonomously. We were also gathering some ideas from like other projects.
Well, for me, I didn't know a lot about a lot of mechanical stuff before this because I was just computer engineering. So now that we're doing the race car stuff and we get to like building the chassis for me, which has been me and Lewis's main job, has been pretty interesting. Sometimes you learn a lot of mechanical engineering concepts and interesting stuff like that.
I don't know what to say. I mean, there's just a lot of moving parts, I guess, and I guess just trying to navigate every single like moment, I guess. It's like, yeah, because like you do sort of learn, like they teach you like there's gonna be like lots of steps that you have to take to like forming, like you set up your steps to build a project and then you go through them one by one, but then just like it goes from head knowledge to like real knowledge because you're like actually working on it like with your hands.
So the process for you was like, the whole process of like what's going to be like in the industry of actually like working with the team
And
and
then
bringing
also
it into reality.
having to test it and then go back and readjust.
And I would say what can go wrong will go wrong. It's like what they were saying before with the motor smoking. That was a day before the first presentation.
Oh, that was scary.
So
that was.
And we were like panicking like crazy when that happened, and
I had to go home and get the other motor.
yeah.
Luckily it worked, but
And then I had to
scary.
install it like the morning before the demo.
Yeah, I had to make like a 9 p.m. I don't know if it was Staples or Best Buy.
Best Buy.
Best Buy.
Yeah,
to
we
get
were
the
on a
cable we
video
needed,
call
and it was
and,
kinda closed, and I didn't know what kind of cable we needed. It
yeah.
was a hassle.
Just had to prepare for the worst.
Silicon Valley.
Yeah.
All night.
Yeah.
Yeah, not here in New Jersey. Are you from California? You worked there? That's cool. Yeah.
You don't go to Fry's. Oh, you gotta go to Fry's. That's huge stuff about.
Yeah, I mean and also we've learned like to have at least like a backup set. That way, in case something goes wrong again, we can just instantly replace it.
So do you have in your, money you spent so far, did that include backup components?
Yes.
Yeah.
That motor was in it, yes. Because it came with like a pack before, thankfully.
Because when you're working with a race car, you have to be ready for crashes. Like it's just part of it, especially when we're testing the like the driving and stuff, just testing it. Well, any other questions?
Thank you so much.
Thank you.
Yeah, thank you.